Thank you very much for the invitation to participate in DART. And I'm presenting joint work with María Ángeles Turro from Universidad Autónoma de Madrid. The spectral problem given by the Schrödinger equation with the potential stationary potential subject to the KdV equation, satisfying an equation of the KdV hierarchy, is a extensively studied problem, and we are presenting one more view on the integration of this problem under Bragg's ideology from 1919. We are looking at the equation as an ordinary differential equation with coefficients depending on the potential and the spectral parameter lambda. Our work is based on mainly in these 4 papers. The Burland and Chaundi 1928 paper relating the commutative pairs of differential operators with algebraic curves. And the paper by Emma Previato, where she uses differential resultants to compute the defining polynomial of the spectral curve. Then we try to understand the approach of Gestesi and Holden about these KdV Schrödinger equations. And we are inspired also by this paper by Yuri Brezhnev, where we studied finite gap potentials, which are a more general case, and where he makes a first attempt to define the Picard-Bessel fields for these equations. We thought that another look, a more appropriate constant field should be considered, maybe in words of Alan Kohns. The field of constant is more elaborated than C. The calculations of physicists are full of examples of constants as coupling constant of electromagnetic interactions, weak and strong interactions where they are constant only by name. What physicists are maybe implicitly doing is extending the scalar field to a field of functions. Well, my plan is to review the conditions, the constraint given by the KdV hierarchy to describe the centralizer of such a Schrödinger operator, then talk about differential resultants and how to use them to compute the Burland-Chaundi polynomials. Then differential sub-resultants to give a factorization algorithm for the Schrödinger operator that admits also a one-parameter form, and use this construction to give the decomposition field the extended version of Picard-Bessel field to this case, which also admits a one-parameter form, and we can use it as a generic case to later do specializations and recover the classical Picard-Bessel fields. So let me start with K is a differential field of 0 characteristic whose field of constants is C, algebraically closed. And how do we read given a potential in K, it satisfies one of the stationary KdV equations. KdV equations are classically known. They are described by differential polynomials in one variable, and it's well known that they can be recursively generated by this recursion or similar recursion operator, which is a pseudo-differential operator. And the question, well, and we can generate more KdV equations making linear combinations of the previous ones. So the question is, given a potential, for what values of constants can we have a solution? This potential is a solution of the KdV equation. So the equation describes a hyperplane in Kn whose intersection we see and is what we are looking at. So we will say that if solution exists, then U tilde is called a KdV potential, and we call the KdV level to the smallest integer s, so that a choice for constants is available. And one can prove that at this first level, there's a unique choice, but of course, in the following levels, there's an infinite number of choices, and we have a flag of constants. To have some examples in mind, just to illustrate the results that I will be presenting, we will consider 3 families of potentials: the rational potentials, Rosen-Morse potential, and a family of elliptic potentials. P is the Weierstrass P function. And so for value of s equal 1, then these potentials are KdV potentials of level 1, and these are the appropriate choices for constants. And for s equal 2, they are KdV potentials of level 2, and we can compute these choices of constants. Well, we have an algorithm that includes these cases, but I will not have time to get into that. Well, so from now on, I will consider a potential US that is KdV potential, and C bar S would be the choice of constants, what we call the basic constants vector. It is well known also that the KdV equations admits lax pair representation. So there are differential operators that whose commutator with the Schrödinger operator equals the KdV equation, even for U to be the generic differential variable. Down here, maybe you can see it from the top, these differential operators are obtained also as linear combinations with the constants of some differential operators that are obtained from the Schrödinger in a recursive manner. Okay, so from now on, we can see that the KdV is Schrödinger operator, as I said, with US a KdV potential and a choice of the basic constant vector. Then replacing those in the KdV equation, we have a solution. That means that these 2 operators, the KdV Schrödinger operator and this operator A2s plus 1, after replacing the potential and the constants by this choice, then these 2 commute. So A2s plus 1 belongs to the centralizer of LS. And in fact, it has an important role. Using a result by Ken Gurdjieff from '83, we can prove that A2s plus 1 and 1 are a basis of the rank 2 free CLS module. And this is the centralizer. So the centralizer is just determined by this operator A and LS. Well, let's compute now the spectral curves using differential resultants. The differential resultants for ordinary differential operators is the simplest case of non-commutative resultant. Is the immediate generalization of the algebraic resultant of 2 polynomials in 1 variable to the non-commutative case. So given P and Q, ordinary differential operators of order n and m, the Sylvester matrix of P and Q is obtained as a coefficient matrix of the extended system, multiplying P by the derivation up to power m minus 1, and multiplying Q by the derivation up to power n minus 1. Then we get an n plus m square matrix whose determinant is the differential resultant. An easy example, here you can see the Sylvester matrix and how when we multiply multiplied by derivation, we have to take into consideration the commutation rule. Of course, there are some main properties that are similar to the ones of the algebraic resultant. The differential resultant belongs to the elimination ideal. This is the ideal generated by P and Q and intersected by the coefficient field K. And the resultant will be 0 if and only if the two differential operators have a common factor on the left. Well, then the famous result by Burnell and Chaundi states that given two differential operators, if they commute, then there exists a polynomial with constant coefficients in lambda mu that is satisfied by the two differential operators. This is called the Burnell-Chaundi polynomial. And Emma Previato proved that it can be computed by means of the differential resultant. If you compute the differential resultant of P minus lambda and Q minus mu, what you obtain is a non-trivial polynomial. And by the properties of the resultants is in this elimination ideal. So what is left is to prove that, in fact, what you get here is a polynomial with constant coefficients. To prove that, this can be done using the Poisson formula for the differential resultant. But I will not go with the proof. And because of belonging to the elimination ideal and having two operators that commute, of course, this polynomial here is satisfied by P and Q. In particular, for the lax pair, the Schrödinger, KdV Schrödinger operator and the operator that determines its centralizer, then we call Fs to the polynomial defined in the spectral curve gamma S. And we can compute it using the resultant. And it's well known that the polynomial has this form, is mu square with a part in lambda that has degree 2s minus 1, even degree. Therefore, this is an irreducible polynomial with coefficients in K. Here, let's look at the example of the Rosen-Morse potential, where these are the polynomials describing the spectral curves. This is also well known. And, well, this should be a plus. And here is just the example of how the Sylvester matrix looks like, but whose computation is a polynomial with constant coefficients. Okay, then in general, if we look at the polynomials P minus lambda and Q minus mu, we think of these two as operators with coefficients in K lambda mu. As operators with these coefficients, they don't have a common factor because the differential resultant of these two operators is a non-zero polynomial. The differential resultant in that case would be a polynomial with n degrees n and m. Well, let me, I will write it later because I want to write it with the lax pair, sorry. Well, the thing is that the differential resultant is a non-trivial polynomial, so they don't have a common factor if we look at them here. But if we consider the square-free part of the differential resultant and assume that it's an irreducible polynomial, then we can consider domains C lambda mu over the ideal in here generated by F, and this other domain, this would be the ideal in this other polynomial ring, and then consider fields of fractions. And over this field, over the field of the curve, then the two operator will have a common factor. And using the sub-resultant theorem, this common factor is given by the south sub-resultant, the first non-zero sub-resultant in the sub-resultant sequence. So if we look now at the lax pair situation, then we saw before that the differential resultant is more things, of course. This is a non-zero polynomial, so these two operator, Ls and A2 s plus 1 minus lambda and minus mu, they will not have a common factor in K with coefficients in K lambda mu. But if we look at the fraction field of this domain, the field of the curve, then with coefficients there, these two will have a common factor and can be computed using the first differential sub-resultant. We prove also that the constant field of this differential field will be C gamma S. This is an important point. And using the first sub-resultant, what we obtain, the quotient of minus phi1 and phi2, this would be a solution of the Riccati equation that corresponds to the Schrödinger operator. This is classical, of course. If we have this factorization, then this term phi s should be a solution of the Riccati equation. But because we are computing it using the first sub-resultant, then phi1 over phi2 is the quotient of two determinants that are determinants of submatrices of that are submatrices of the Sylvester matrix. So we have a closed form for this computation. So here is an example with s equal 1, where the factor, the common factor of these two operators would be this one, and these coefficients can be computed as determinants of these two matrices. Of course, in the one for this coefficient, there is a mu and no mu appears in the other one. That gives you an idea why we always get the same expression here, where this phi s is the quotient of mu plus some alpha of lambda over phi 2 of lambda. And it's important to note that this phi, because of the shape, is always non-zero in the field of the curve, and its denominator, which is a polynomial of degree s, is always non-zero. Okay, so then using this, we can give an algorithm to compute the factor of the KdV Schrödinger operator. So we take Ls and the A2s plus 1, then compute the spectral curve, the polynomial that describes the spectral curve. Over the field of the curve, we compute the differential sub-resultant, and the quotient of its coefficients would be the independent term of the factor. So this method can be applied for any curve, any spectral curve that we obtain. And in the three families of examples, these are computations we made with the Maple 18. So we programmed here the differential resultant and sub-resultant. And well, they may be big expressions, but there's no, it's straightforward to make the computation. Well, once we have the expressions for the factors for phi s, then we wonder if we can obtain a one-parameter form of the factors. Of course, this would depend on the parametrization, on a notion of parametrization of the curve to express lambda and mu in terms of a single parameter. So here is the definition of parametrization that we would like to use. We would like to use a global parametrization. So an affine algebraic curve is parameterizable if there are meromorphic functions G1 and G2 in a subdomain of P1, such that for almost all values of the parameter, the parametrization is a point on the curve, and conversely, for all but a finite number of points on the curve, we have a value of the parameter that gives us this point in the curve. So this is what we call a global parametrization, and is a result by Verdon and Ngo that this exists. Another thing is how to compute it, or do we have algorithms to compute it? So we will assume that the parameter is an algebraic indeterminate over the field of coefficients that contains the potential of our KdV Schrödinger equation. Then would be a constant with respect to the derivation. And in this way, if we consider the fraction field, the field of rational functions in G1 and G2 over K, then C of this other field of fractions would be the field of constants under this assumption. And we can establish an isomorphism, rho, sending lambda to substituting lambda and mu, or replacing them by the parametrization. Then in the genus 0 case, of course, we have rational functions, and there are well-known algorithms, symbolic algorithms, to parameterize them, obtain a rational parametrization. For example, the algorithms by Franz Winkler and Rafael Sendra. In the genus 1 case, one can obtain parametrization in terms of curves, and more difficult, of course, is the case genus greater or equal than 2, where the field will be contained in the field of automorphic functions, but as far as we know, there are no algorithms. There are some methods to maybe to approach the parametrization, but no symbolic algorithms as far as we know. If you know some, we'll be happy to approach examples using them. So just to look at one of these families, in the case of Rosen-Morse potential, note that the curves that we obtain, they are rational curves. Then, and in fact, they admit this easy polynomial parametrization. Then we can give an expression of the factors in one parameter form. Here, the W is e to the 2x, but all the coefficients. So this expression would depend on the potential. In fact, this potential belongs to the field C with the exponential function, and also of the parameter of the curve. Okay, then to finish my talk, I have 10 more minutes. Then I will give the definition of decomposition field. So we call a differential field extension of the field of the curve a decomposition field of this equation over the curve to the differential field extension generated by a fundamental set of solutions by one psi 2. And it's not enough. On top of it, we have to demand that this field extension has the same field of constants, C of gamma S. So this is, in fact, the difficult part, to show that the same field of constants is obtained. So to obtain a fundamental set of solutions, we have Vs, which was mu plus alpha over phi 2, and we can exchange mu by minus mu to have another point on the curve and obtain another factorization that gives us another solution. And one can prove that these two solutions are in fact a fundamental system, because the Wronskian over this product is a non-zero element on the field of the curve. Is this element 2 mu over phi 2, which is now 0 in K of gamma S. On top of it, from here, we can obtain that the product of the two solutions is in fact an element of the field of the curve. Therefore, it would be enough to consider the Liouvillean extension of the field of the curve by the first solution, phi s. So this would be the Liouvillean extension of this first order operator. So as a conclusion, we have, this proves that the decomposition, this would be the decomposition field of the curve, is a Liouvillean extension whose field of constants is C of gamma S, the same field of constants of the equation. What about the one parameter form? If we can obtain a global parametrization of the curve, then we can consider the one parameter form of the factorization and use that to get a one parameter closed form of the solutions. And this field would be isomorphic, the one parameter version of the decomposition field of the equation. So here is the previous example of the Rosen-Morse potentials. Replacing, this would be the closed forms using the one parameter factorization. One important observation is in terms of computations. If we want to integrate this equation in K gamma S, but not in the one parameter form, in terms of lambda and mu and over the curve, then there are no symbolic algorithms. We have them in one parameter form, then one can use, for example, the symbolic integration result by Manuel Bronstein to obtain the solutions. And to finish, I would like to point out that this generic situation, because we have been dealing with lambda generic so far, falls into the specialization when we take lambda equal lambda 0 in the case of points of the curve with mu 0 different from 0. We have to avoid, of course, the singular points of the curve and other points. And in this case, then replacing lambda and mu by lambda 0 mu 0, and in particular by its one parameter form, then we get the solutions. We recover the solutions of the spectral problem for a choice of the parameter, for all choices that don't fall into this case. Then we will recover the Picard-Bézieux extensions. In this case, recall that the field K was the C of the exponential, and then the Picard-Bézieux extension will be this one. But of course, not in this example, we can see that after specialization, these extensions are not always transcendental. So here is these are all the possibilities where you can get no extension, a finite algebraic extension, or a proper transcendental extension. As a conclusion, we develop a general framework to develop effective computation methods to study stationary KdV Schrödinger operators. We computed closed formulas for the factors and solutions of this operator using symbolic computation. And these methods can be extended to develop similar methods for other finite gap operators. We have generalized the concept of Picard-Bézier extension to this case. And what we plan to do next is to approach the general specialization and look further into the case of elliptic potentials and compare with existing results on Picard-Bézier extensions of comparatively recent papers by Primitivo Acosta and Juan Morales and Jacques Arthur Vail, and also the paper by Yuri Brezhnev. Well, this is all, and I would like to thank all the members of the Integrability Madrid seminar directed by Juan Morales, where we have been looking at these problems from 2002. And if you are interested in this work, we have a preprint in the archive. Thank you very much. Well, the description of the decomposition field, the question. So the question is that the examples we are showing in the talk are the genus 0 cases. And if I can say something about the hyperelliptic case, which is the difficult case. So, what am I? Here. So I wanted to say that I showed these examples of elliptic potentials, and S is greater or equal than 2, then we have genus greater or equal than 2. We can give the expression of the factors over the field of the curve, no problem, in this form, in terms of lambda mu. Of course, the difficult part is to keep them in one parameter form. Then the rest of the examples that I showed in one parameter form were the rational cases, because what is under this method that that I just talked about, the difficult part would be to give a parameterization of the curve in the case of hyperelliptic curves. Maybe you know of some approach to obtain these parameterizations. I think I'm aware of your work about sigma functions and solutions of the KdV equations. But as far as I understand, this is approaching the inverse spectral problem to obtain potentials and solutions. We intend to approach so far only the direct spectral problem. We are given a potential, and we would like to, we try to give algorithms to obtain the closed form solutions in one parameter form, depending on having a parameterization.